In this video, we will discuss the most common reaction orders, 0, first, and second order, by introducing integrated rate laws. Another way to view an integrated rate law is that they are the concentration changes with time. We will also talk about applications of these integrated rate laws by talking about half-lives. First, let's define some terms we have already introduced. A reaction is zero order in a reactant if the change in concentration of that reactant produces no effect. A reaction is first order if doubling the concentration causes the rate to double. A reaction is nth order if doubling the reaction causes a 2 to the n increase in rate. So therefore, a reaction is second order if doubling the concentration causes a 4-fold increase in rate. We integrate rate laws to give convenient equations in reactant concentrations as a function of time. There are two different types of rate laws, and the rates in both of these rate laws equal each other. Take, for example, the reaction where a reactant A decomposes into a product P. The rate law equation is that negative the change in concentration of A per delta time equals the change in concentration of P per delta time. The negative is in this equation because reactants' concentration decrease as a reaction proceeds and to obtain an overall positive value for the reaction rate. Another equation for the rate law is that the rate equals the rate constant times the concentration of A raised to some power. The first way to determine this power is by using the method of initial rates, which uses a reaction with different initial concentration of reactants, and then looking at the resulting changes in initial rates. Another way to determine the order of the reactants is to consider the integrated rate laws. We will consider each one, starting with the least complex. For a zero-order reaction, the reaction rate does not depend on, is independent of, the reactant concentration. The zero-order reaction has a zero-order rate law. Rate equals K, the rate constant, times the concentration of A raised to the zero power. And since any number raised to the zero power is 1, rate equals K. The rate in the rate law is the same rate in the reaction rate expression. So therefore, rate equals negative the concentration of A divided by delta T, which also equals K. If we do a little calculus by taking the derivative of this equation, integrating it, and then evaluating the integral, we end up with the concentration of A at some point in time of the reaction minus the initial concentration of A equals negative K times time. If we add the initial concentration of A to both sides, we end up with the concentration of A at a certain point in the reaction equals negative K times time plus the initial concentration of A. This equation looks like a straight line equation, y equals mx plus b. So therefore, for a zero-order reaction, a graph of reactant concentration on the vertical axis, y-axis, versus time on the horizontal axis, x-axis, gives a straight line with a slope equal to negative k. For a first-order reaction, the reaction rate is directly proportional to the reactant concentration. So therefore, the rate law looks like rate equals K, the rate constant, times the concentration of A. Set it equal to our reaction rate expression. We have rate equals negative the concentration of A divided by delta time, which also equals K times the concentration of A. Again, do some calculus by taking the derivative of this equation, integrating it, and then evaluating the integral, and you come up with the first order integrated rate law. The natural log, ln, of the concentration of A at a certain time divided by the natural log of the concentration of A at time 0 equals negative K times time. If you rearrange this equation by utilizing the rules of natural logs, we end up with the natural log of the concentration of A at a certain point equals negative K times time plus the natural log of the initial concentration of A. This again is related to the equation of a straight line. A plot of the natural log of the concentration of A on the vertical axis versus time on the horizontal axis is a straight line with slope equal to negative k and y-intercept equal to the natural log of the initial concentration of A. Another way to write the first order integrated rate law is by taking the exponent of both sides. Then the concentration of reactant A at some time equals the concentration of the initial amount of A times the exponent of negative K times time. This law takes many forms, but they are all equivalent. If we run the same analysis with a second-order reaction with just one reactant and set its rate law and the reaction rate expression equal to each other, the rate law looks like rate equals K, the rate constant, times the concentration of A squared. Set it equal to our reaction rate expression we have, rate equals the negative the concentration of A divided by delta time, which also equals K times the concentration of A squared. Again, do some calculus by taking the derivative of this equation, integrating it, and then evaluating the integral, and you come up with the equation 1 over the concentration of A at some time equals K times time plus 1 over the initial concentration of A. For a second-order reaction with just one reactant, a plot of 1 over the concentration of reactant on the vertical axis versus time on the horizontal axis is a straight line with slope equal to K and y-intercept equal to 1 over the initial concentration of reactant. For a second-order reaction, a plot of the natural log of the concentration of reactant versus time and the concentration of reactant versus time are not the most linear. What if we have an overall second-order reaction, but we have two reactants that are first-order in both? Something like A plus B results in P. This type of situation is complicated to write an integrated rate law for, unless one of the two reactants is in large excess. In these cases, the excess reactant's concentration remains virtually constant over the course of the reaction. For our example, let's say that a reactant A is in large excess. Then our original rate law, rate equals the rate constant times the concentration of A times the concentration of B, becomes the rate equals a pseudo-rate constant times the concentration of B. The pseudo-rate constant then equals the real rate constant times the initial concentration of A. Because A will not change during the reaction, so the initial concentration is also the final concentration of A. This new rate law is a pseudo-first-order rate law because it appears to follow first-order kinetics. A pseudo-first-order reaction has the same integrated rate law as a first-order reaction, but the rate of the pseudo-first-order reaction depends on the concentration of more than one reactant. The half-life of a reaction is the time it takes for the initial concentration of a reactant to drop to half its original value. View this graph for a visual representation of what half-life is. For a zero-order reaction, half-life equals the initial concentration of the reactant divided by 2 times the rate constant. For a first-order process, mathematically the equation is the half-life equals negative natural log of 1/2 divided by K. Half-life then equals 0.693 divided by K. For a second-order reaction, half-life depends on the initial concentration. For a second-order reaction with only one reactant, such as A results in P, the half-life equals 1 over the rate constant times the initial concentration of A. This figure will summarize all we have learned about these integrated rate laws, their graphs, and their equations. This figure and the tables only relates to reactions involving a single reactant, such as A producing P. Pause the video now to inspect this table to see if you have understood everything that we have covered in this video. Now we will work on some example problems using the concepts discussed in this video. 1. Nitrogen trioxide decomposes to NO2 and O2 in the following reaction. 2NO3 gas results in 2NO2 gas plus O2 gas. The following data were collected at 298 Kelvin. A. What is the order of the reaction? You can find this by plotting the concentration of NO3 versus time, the natural log of the concentration of NO3 versus time, and 1 over the concentration of NO3 versus time, and deciding which one is the straight line. B. Write the rate law expression for this reaction. C. Find the value in units of the rate constant for this reaction. D. What is the concentration of NO3 after 78.0 minutes? E. What is the half-life for this reaction? To graph this data, it is easiest to use Excel. Open a new Excel file, type in the data just as it is shown in the table. To type in scientific notation, it is easiest to type in the digits, then an E, then the exponent. Then highlight the data and insert a scatter plot with smooth lines and markers, and right-click on the line and select Add Trend Line. In the Format Trend Line box that appears, click Linear Line and then Display Equation on the chart, and display R² value on chart. The R² value is a measure of how linear the line is, and an R² value of 1 is the closest you can get to a straight line. Pause the video now to see if you can get this first chart. Then, to calculate the other data, copy and paste the time data into the next column. Then, in the column next to that, type in equals ln open parentheses, and then move your mouse into the first concentration box, and then type close parentheses. Then press Enter. To get the rest of the natural log information calculated, highlight and drag down this box into the rest of the column. Then do the same thing for the 1 over concentration data by typing in equals 1 / open parentheses, and then move your mouse into the first concentration box, and then type close parentheses. Then press Enter. You need to use the first concentration column. Do not use the natural log of concentration column. Then follow the graphing instructions to make separate graphs of this time and natural log in time and 1 over the concentration data. When you have all of your graphs made, compare their R² values. The graph of a zero-order reaction of the concentration of NO3 versus time has an R² value of 0.99674. The graph of a first-order reaction of natural log of the concentration of NO3 versus time has an R² value of 0.99919. The graph of a second-order reaction of 1 over the concentration of NO3 versus time has an R² value of 1. The R² value is closest to 1 for the 1 over concentration versus time graph, so this means that this is a second-order reaction. For part B, write the rate law expression. We know that it is second order, and that the kinetics of a reaction only depend on the reactants. So the rate law is rate equals K, the rate constant, times the concentration of NO3 squared. To find the rate constant in part C, we know that for a second order reaction with just one reactant, a plot of 1 over the concentration of NO3 on the vertical axis versus time on the horizontal axis is a straight line with slope equal to K and y-intercept equal to 1 over the initial concentration of NO3. So view the equation of the line on the graph you just drew. The equation is y equals 0.3202x plus 680.24. So therefore, our rate constant equals the slope, which is 0.3202. To find the units of the rate constant, consider our rate law expression. Rate, which will be in the units of millimolar per minute, equals K times the concentration squared, which will be millimolar squared. The millimolar that was on top will cancel out with 1 of the millimolar that was on the bottom. And the units of K are 1 over millimolar times minute. In part D, to find the concentration of NO3 after 78.0 minutes, we will use the second-order integrated rate law that we derived in this video, which is 1 over the concentration of NO3 at some time equals K times time plus 1 over the concentration of the initial concentration of NO3. We know our initial concentration of NO3. It is just the concentration of the reactant at time 0. We also know our value of K from part C, so plug what we know into our equation. We have 1 over the concentration of NO3 at 78.0 minutes equals 0.3202 1 over millimolar times minute times 78.0 minutes plus 1 over 1.470 times 10 to the negative 3 millimolar. Our minutes will cancel out, and we have 1 over the concentration of NO3 equals 705.24 1 over millimolar. So the concentration of NO3 after 78.0 minutes equals 1.418 times 10 to the negative 3 millimolar. In Part E, to find the half-life for this reaction, use the half-life equation for second-order reactions, which is for a second-order reaction with only one reactant, the half-life equals 1 over the rate constant times the initial concentration of NO3. Therefore, the half-life equals 1 over 0.3202 and 1 over millimolar times minute times 1.470 times 10 to the negative 3 millimolar. The millimolar cancels out. Our half-life comes out to be 2,124, and for the units, all we are left with is 1 over minutes, which equals minutes. 2. Carbon-14 undergoes beta particle decay and follows first-order kinetics. The half-life for this process is 5,730 years, and this isotope can be used to date artifacts. The C14 content of an ancient piece of wood was found to have 3/10 of that in living trees, indicating 70% of the C14 had decayed. How old is that piece of wood? We know that for any process, the half-life of a reaction is the time it takes for the initial concentration of a reactant to drop to half its original value. For a first-order process, the equation is T 1/2 equals 0.693 divided by K. So therefore, K, the rate constant, equals 0.693 divided by T 1/2. K equals 0.693 divided by 5,730 years, which equals 1.209 times 10 to the negative 4, 1 over years. Now we will need to use our integrated first-order rate law, which is the natural log of the concentration of A divided by the concentration of A at time 0 equals negative K times time. In this question, they are asking for the time, or the age, of the piece of wood. If we assume at time 0 we had 100% of the C14 content, at the time we are now, we only have 30% of the C14 content, because 70% has decayed. So our concentration of A divided by our concentration of A at time 0 is 0.30. Then our equation looks like the natural log of 0.30 equals negative 1.209 times 10 to the negative 4, 1 over years times our time. Our time is therefore equal to the natural log of 0.30 divided by negative 1.209 times 10 to the negative 4, 1 over years. The time, or the age of the wood, is therefore 9,958 years old. 3. For a specific first-order reaction, it takes 13.0 minutes for the reactant concentration to drop from 0.250 molar to 0.160 molar. A. What is the rate constant? B. How long will it take for the reactant concentration to be 0.100 molar? C. What is the half-life when the reactant concentration is 0.100 molar? Since it tells you that this is a first-order reaction, we already know our rate law, which is the natural log, ln, of the concentration of A at a certain time equals negative K times time plus the natural log of the concentration of A at time 0. The problem tells you that the reaction starts at 0.250 molar and ends at 0.160 molar in 13.0 minutes. Therefore, the concentration at time 0 equals 0.250 molar, and 13.0 minutes later is 0.160 molar. We can plug these numbers into the equation to find the rate constant, our answer to Part A. The natural log of 0.160 equals the negative of our K times 13.0 minutes plus the natural log of 0.250. We will drop both of the units of molarity for our concentrations because the natural log needs to be taken care of as a unitless number. K equals natural log of 0.160 minus the natural log of 0.250 divided by negative 13.0 minutes, which equals 0.0343 1 over minute. For letter B, they are asking for the time when the reactant concentration is going to be at 0.100 molar. Use the same equation as before. The natural log, ln, of the concentration of A at a certain time equals negative K times time plus the natural log of the concentration of A at time 0, and we are looking for time. The initial concentration will still be 0.250 molar, and the concentration at time t is 0.100 molar. And we just calculated K, which equals 0.0343 1/minute. Plug the values into the equation and you will get the natural log of 0.100 equals the negative of 0.0343 1/minute times the time plus the natural log of 0.250. Time equals natural log of 0.100 minus the natural log of 0.250 divided by the negative of 0.0343 1/minute, which equals 26.7 minutes. Does this answer make sense? Yes, it takes a longer time, 26.7 minutes, to drop to 0.100 molar than it does 13 minutes to drop to 0.160 molar. For letter C, they are asking for the half-life when the reactant concentration is 0.100 molar. The half-life equation is T1/2 equals 0.693 divided by K. So the half-life equals 0.693 divided by 0.0343 over 1 minute, which equals 20.2 minutes.